consider the schematic. This, so you see over here, you have the schematic diagram of an N-channel enhancement mode MOSFET. So by now you are familiar, if you have seen the part 1 of the this lecture videos, you see that this enhancement mode that means that you need to apply a certain gate to substrate voltage. Okay, now since you see that your substrate material is p-type, so the gate is going to be connected to the positive end of the supply, and then the negative is connected to the bottom of the substrate. So what happens is, so this is enhancement mode. Enhancement mode means you are going to connect your metal gate. So you have this metal gate of width W, okay, and the length is L. So this metal gate, which is aluminum or highly doped polycrystalline silicon, is going to be connected to the VGS, the battery source over here externally. Why do we need this external biasing supply? Is that we are interested to have a channel or a channel that or a space charge region, okay, or inversion layer as we have seen previously. So you see that for a p-type substrate, how we created the this inversion layer consisting of minority carriers in the p-type substrate is through the application of this gate to substrate voltage VGS. So this VGS is basically it's not gate to source, it's gate to substrate. I'm referring this VGS. So if you're going to increase your gate to substrate voltage, what's going to happen is you're going to vary this width, the channel width, and there will be more and more minority carriers because the positively charged holes are going to be attracted. They are going to be accumulated at the bottom of the substrate where the negative of the battery is connected. Okay, so this you will see in the schematic 5 that this channel, the establishment of the channel is going to favor the current which is going to flow from source to drain. You see over here in this elaborate diagram, there is a metal gate, then there is an oxide of thickness TOX. Okay, the width of the this gate is W, metal gate is W, and the length is the small. This length is capital L. Okay, and this is typically in the order of 1 micrometer. So this makes the device very small. Making a very large scale integration, highly dense MOSFET based digital electronics possible on a single IC. So that's the idea. So anyways, you see two more besides the MOS capacitor configuration, you see two more metals over here. So two more terminals. One is the source terminal and the other is the drain terminal. Okay, this is your source and drain, and you have the connection over here. You have VDS, that's drain to source basically. So the current in a MOSFET is a result of the flow of the charge in the inversion layer. So that's why we need to supply the voltage, and that the application of the voltage, this is now known as enhancement mode. So once you apply the voltage, you create the channel, and if you can guess this correctly, the channel will be n-type, will consist of negatively charged, will allow negative charge carriers to flow from, that's the source to drain. Okay, so this channel is going to favor the flow. So basically this depletion width is being regulated or controlled by the gate to substrate voltage. Okay, so that's how you're going to control the current in the MOSFET. So this figure 5a basically is showing you a simplified cross section of MOS field effect transistor. Okay, and the gate oxide, it shows the gate. Okay, it shows the oxide, and you have a p-type substrate over here. Okay, so this is your gate, this is your oxide, which is going to separate your semiconductor to metal. Okay, so there will be an interface regions. So these are p-substrate regions. So they are the same as that of MOS capacitors that you've seen earlier. And in addition, we have two N regions. So one is the source and the other is the drain. So the current in a MOSFET is the result of the flow of charge in the inversion layer. So this inversion layer is very important. Okay, so to have a flow from source to drain, you need to have a channel. Okay, if there is no channel, or if you don't have any gate to gate to substrate um, supply, well, then both the source and the drain are separated by p-type substrate. Okay, so there is no flow of charge. There is no channel. There is no flow of charge. So no current. Okay, so this current has to be regulated by the application of VGS, okay, gate to substrate voltage. So you need a channel region. So this inversion layer, basically this inversion layer is being referred to as the channel region, which is adjacent to the oxide and semiconductor interface. This is your oxide and semiconductor interface. Okay, so the gate could be polycrystalline. It could be a polygate. Then you have a polycrystalline silicon. Then you have gate oxide over here. You have source and drain metals. Okay, so that's how you are supplying the VGS over here. This is positive, negative, depending on the type of substrate. If this is p-type, remember that the gate has to be positively. It has to be connected with the positive terminal of the battery. So it has the positive charges. The negative charges come at the bottom of the MOSFET plate. So the holes are attracted. The holes will be attracted towards the bottom, and the minority carriers will form the channel. Okay, that's the idea. Okay, so as I mentioned before, the length and the width, the dimensions are um, the, the channel length and the width of the channel are defined by these parameters L and W, and the channel width, the channel length for typical IC MOSFET is less than 1 micrometers, which means that the MOSFETs are small devices. So, and the thickness of oxide is typically in the order of 400 angstroms or less, so which again shows you have a very small device. The diagram 5a is a simplified sketch of the basic structure of the transistor. Figure 5b shows the more detailed cross section of MOSFET. Okay, this is your 5b. So this is the more detailed cross section. Anyways, the idea is you have you have three terminals. This is a three-terminal device. So you have a gate. Okay, you have your drain metal. You have your source metal, and between your gate and the semiconductor material, there is oxide, okay, and there is a gate oxide interface which is being shown over here. So, MOSFET, detailed cross section for MOSFET fabricated into an IC configuration. So a thick oxide called the field oxide is deposited outside the area in which the metal interconnect lines are formed. The gate material is usually heavily doped polysilicon. It could be aluminum as well. But commonly it's heavily doped silicon. Even though the actual structure of MOSFET may be fairly complex, but the simplified diagram is good enough to develop the basic characteristic of the transistors, as we're going to see the IV characteristic. To start with the basic operation of transistor, you see once again, if I repeat the steps, if you're not going to have any VGS, any connection between gate and the substrate body, okay, no connection, then these two terminals, source and drain, they are separated by the p-type substrate. There is no channel, there is no flow of electrons. So with zero bias applied to the gate, the source and drain terminals are separated by the p regions, as shown in 6a, this figure. So this is equivalent to back-to-back diodes. Okay, so basically there is no current flowing because the junction is not forward biased. There is no channel. So the current in this case is essentially zero. If a large enough positive gate voltage, why positive? Because you have p-type. Just remember this. If you have a p-type substrate, just apply a positive to negative. Okay. So for example, over here, once again, I'm going to have this positive terminal of the battery, and I'm going to have a negative terminal of the battery. So and that's how I'm going to make the connection of the external VGS battery to have charges on the plate and on the substrate. And due to this, I'll have the accumulation of positive holes on the bottom of the substrate. Okay, and owing to the minority negatively charged carriers, I'm going to have some depletion negative space charge region, uh, which is not going to consist of majority carriers of the p-type, which are the holes. So due to this establishment of this channel, you are going to have a current. Okay, so if a large enough positive gate voltage is applied, the electron inversion layer is created. This is your electron inversion layer over here, the same thing. Okay, and this is created at the oxide semiconductor interface, and this layer connects the N source to N drain. Okay, so these both the source and drain are N-type materials. Okay, consisting of negatively charged um, carriers. So That's how you're going to conduct. You're going to have a conduction of current from source to drain. So the current can be generated between the source and drain terminals since the voltage must be applied to the gate to create the inversion charge. This transistor is called enhancement Mosfet. Enhancement mode Mosfet means that you need a supply voltage, okay, and this device is also called N-channel Mosfet because the carriers in the inversion layer are electrons. Okay, so you see over here you have electrons. These are electron negatively charged. So this is NMOS. Okay. Uh, the source terminal supplies so the source terminal supplies carriers that flow through the channel, and the drain terminal allows the carriers to drain from the channel. So for the N-channel NMOS, the electron flow from the source to drain with an applied drain to source voltage, which means the conventional current is the other way around, from drain. It enters the drain and leaves the source. The conventional current is the direction of the conventional current is taken always as an opposite to the flow of charge carriers. The magnitude of the current is a function of the amount of the charges in the inversion layer, which in turn is a function of the applied gate voltage. Since the gate terminal is separated from the channel by an oxide or an insulator, there is no gate current. Okay, so you're not going to flow any current through this oxide. You have the oxide over here. You remember, this is your with a certain thickness of TOX. This oxide separates gate and the substrate. So there's no flow of current here. The flow of current is through the channel. Okay, this is how the this current is being flowing from source to drain. Nothing happens. No current is flowing from gate to the substrate or the semiconductor body. Okay. Similarly, since the channel and the substrate are separated by a space charge region, okay, there is essentially no current through the substrate. So through the substrate, there's no current, okay, because the channel and the substrate, as you've seen previously, the channel and the substrate, they don't have any flow of charge carriers, okay, due to the due to the space charge region, okay. There's no flow of current, so neither there is any current flowing in the substrate, neither there's any current flowing in the gate to the substrate body, okay. So the only current that flows is either from source to drain, drain to source, okay, if you're going to consider the conventional direction of the current, and that current flow is through the inversion layer or through the channel, and this is your channel or the inversion layer. So over here, this is your inversion layer.